Okay, today we're going to take some first steps towards understanding how we would approximate integrals, a numerical approximation. If you ask a calculator, a TI-83 or 84 has a command that evaluates a definite integral. I can ask it to integrate sine x from 10 to 17 or anything, at any function. It's not actually finding an antiderivative and plugging in the endpoints. What it's really doing is doing a numerical approximation. A much more robust one than what we'll be looking at, but these are the first steps towards understanding what's really happening. And there's three that we're going to look at. We're going to look at the midpoint rule, and the trapezoid, and then the third is Simpson's rule. And these are three different ways of approximating the area under a curve in a way that really only involves addition, adding, subtracting, multiplying, and dividing, which is all that a calculator can do. They do get progressively harder to understand the formulas, but also progressively more accurate with less calculations, which is what we really want in a calculator or a computer program. So let's start with the midpoint. Here's really what we're doing. We're taking some curve, f at x. We're evaluating this area under the curve from A to B. And what we're going to do is we're going to break the curve up. So think about it sort of like a Riemann sum. Right? For a Riemann sum, what do? We break the curve up into a bunch of different rectangles and then add up the areas of the rectangles. So let me just remind you of how that Riemann sum went. If I had a Riemann sum, then we would do something like that. We would break this up into n subintervals. So we're given n, the number of subintervals. In a Riemann sum, what we would do is we would take the area of each of these, which is the length here, delta x, and then we would multiply by the height, which is the function value. So we would have the function value at at one of these things. So remember, I don't want to go through the whole process of Riemann sum. We'll see what's happening with these things, but x sub I means the ith x value. So a is the 0th x value. This is x sub 1. This is x sub 2, and so on and so on and so on, until b is the nth x value. So we break this up, we look at the function value at the ith x value, multiply that by delta x, that is length times height. And so that's the area. We add this all up from the first value to the nth value. This one, as it's written, is actually a right Riemann sum, because we would be looking at the right-hand side. We could go from x0 to n minus 1 to look at the left-hand side. That's the Riemann sum, the very first approximation. A midpoint approximation uses the same basic setup, but we're not going to be using a left or a right. Instead, we want to look at the same idea. So we still have A, we still have B, we still have x sub I in the middle, but instead of evaluating the function at all of these points along the curve that we saw there, we're going to evaluate the function. So we have x1, x2, x3, all the way up to xn. I want to actually go in between each of these points. And so what that's going to do is sort of make a contribution from the left-hand side and the right-hand side. It's really the average of the left Riemann sum and the right Riemann sum with less calculations. So what I want to do is go up inside the two of them together. So if I had x0 and x1, we're going to go all the way up to here, and we get something that sort of splits the difference between the right Riemann sum and the left Riemann sum. So if we go all the way up here in the middle of these two things, We're going to have something that's above the curve, something that's below the curve, and so for that reason it's actually a better approximation. The left Riemann sums over here were way below the curve. The right ones would have been above. This gets me some balancing out between the two. So that's the big idea with a midpoint rule. We're going to use these midpoints. Midpoint is easy to come up with. What is the midpoint of any two numbers? Add them up and divide by 2. So this height up here will be f at xi. Well, let's look at it like this. So we're going to look at it. I'll write the formula down, then we'll talk about it. Xi minus 1 plus xi divided by 2. So when I say the I minus 1 and the ith, I just mean one to the left and then one to the right. And then we're dividing it by 2. So this is the function at the midpoint in between these two things. We're still going to be multiplying by delta x because delta x is still the length across the bottom. So that still gets me the area of each of those curves. And then we'll add these things up from I equals 1 all the way to n. Let's look at an example like that. They're not too hard. They do if we have much more than just a few. If n gets big, it gets very tedious to do. So we're going to, generally speaking, have small values of n, but they're not hard at that point. So let's just look at one example of that. So this is our midpoint rule. Our formula that we use is I equal 1 to n of f at xi minus 1 plus xi all over 2 multiplied by delta x. For example, let's integrate e to the x. Well, let's not even go e to the x. Let's just say okay, we can go e to the x dx from 0 to 4, and let's let n equal 2 subintervals. So my picture is going to look like this. This is going to be 4. This is going to be 0. If I'm saying 2 subintervals, that means that I'm going to just split this distance in half. And then we're going to look at the midpoint of the left one, and we're going to look at the midpoint of the right one. And we want the area of those two rectangles, and that's an approximation for the area of the actual curve. So what the first step is to do is to come up with our x values. We want x0, x1, x2, and so on. Right, so x0 is always the a, which is 0 in this case. The last x value, in this case since it's n equal 2, will be x2, is always the b term, which in this case is 4. So these limits of integration will always be the first x value and the last x value. Then we just have to go in between. Since I want a total of 2 subintervals, there's only going to be one thing in between. So the distance is the total length, so delta x in this case, or in all cases, is b minus a over n. Delta x is the total length divided by the number of subintervals. In this case, that's 4 minus 0 over 2, which is 2, which means that I have to start here and move up 2 units. And that's what we would do in a generic case, not just a simple one like we see here. So x1 will be 2 more than 0, which is 2, right in between the two pieces. Now I have x0, I have x1, and I have x2. So I simply apply the formula that we see right here. So that will be sum of I equals 1 all the way up to n, but n is just 2 in this case, of f at xi minus 1 plus xi all over 2 times delta x. What does that mean in this case? Well, we can just look at the picture and see what's really happening here. What we want is, this is the midpoint of the first one. X equal, or 1 is the midpoint of the first. 3 is the midpoint of the second. So what I want is f at 1 times delta x, and delta x was 2, plus f at 3 times delta x, which is 2. So 1, actually we can figure this out, right? If I put I equal 1 in here, this is x0 plus x1. x0 plus x1 is 2, divided by 2 is 1. So that's where this 1 is coming from. This is 0 plus 1 divided by, x0 plus x1 divided by 2. That's what's happening right in there. And that's delta x. And this is f at x1 plus x2 divided by 2. x1 plus x2 is 6 divided by 2 makes 3. So if we put that together, f at 1 is e to the first power, so that's 2e. F at 3 is e cubed, so that's going to be plus 2e cubed. And that is my approximation. All right, let's look at the trapezoid rule. As it sounds like, what we're going to do is we're going to use trapezoids rather than rectangles. And you should be fairly easily convinced that if we do that, if we use a trapezoid, we're going to get something which is a better approximation. So if this is A and this is B, and I break this up into a bunch of subintervals as before, the left hand would be a way under, left-hand Riemann sum would be a very underrepresentative, the right hand would be a very overrepresentative. The midpoint is better because I have a little bit of over and a little bit of under, but instead what we're going to do is we're just going to make this into a full trapezoid. We're going to essentially make this into a straight line, use the area of a trapezoid formula, and we get a much better approximation. We don't have to worry about so much over and under that's happening. Let's remember what the area of a trapezoid is. If I have a trapezoid, the area is the height times the average of the bases. So height times b1 plus b2 over 2. That's the area. The way our trapezoid is oriented means that it looks more like this. All right, so I'm going to actually think about turning that on the side. This is going to be B1, this is going to be B2, and this is going to be H. We're in a little bit of luck here because because these things are always horizontal, and the way we draw our trapezoids, H will always be delta x. H is always going to be delta x. We're also in luck because the base here is exactly the function height evaluated at x0 or x1 or x2 or x3. So this one in this picture will be x sub I minus 1, and this will be x sub I itself. So one x value and then the next x value together make the two sides of the trapezoid. So what we'll end up getting for the area of some trapezoid in the middle will be h times, so that's delta x, I'll put that on the right hand side, so that will be the function value f at xi minus 1 plus f at xi, all divided by 2, so I'm going to actually write that as divided by 2 separately, and we'll see why in a second. Then all multiplied by delta x. So that's b1, that's b2, and then all over 2. And then that's the height. So this is just one trapezoid. That's just one of the trapezoids. But then we need to add them all up. We're where I goes from 1 to n. So we add up all n of our trapezoids. And that's fine, that's good, but we can do a little bit of algebra here to make our life even a little bit easier. And so let's apply some algebra to this formula here to make a final formula that's actually easier to work with, and then we'll look at some examples. So if I started to write out what we have for this formula, when I plug in I equals 1, we'll get f sub 0 over f at x0 over 2. So that's f at xo over 2 plus f at x1 over 2. And then we're going to have, when I plug in x1, I'll get f at x, when I plug I equal 2 in, I'll get f at x1 plus f at x2. So that will be plus f at x1 over 2 plus f at x2 over 2. And so on and so on and so on. And the whole point is, and at the very end, when I plug n in, I'll have n minus 1, and I'll have n. And the idea here is that this is the same as this. And so when I add these up, 1/2 of f at x1 is plus 1/2 of f at x1 is f at x1. The same thing will happen with f at x2. There's two versions of it, so when we add them up, it just becomes f at x2. The only ones that don't have a match are the very first one and the very last one. And so that will make f at x0 all over 2 plus this one and this one combined together to make f at x1 plus f at x2, because that one will also combine together, plus until the very end, the very last thing that we'll have is f at xn over 2. So the first one and the last one have a divided by 2, all the middle ones paired up so that they don't have a divided by 2, and I can write that in summation notation as f at xo over 2 plus the sum of all of these things, but all of these things are up to and including f at xn minus 1. So this is actually from I equals 1 to n minus 1 of f at xi, then plus at the end f at xn all over 2. And I failed to put this in my formulas here, but we also had a delta x here, remember, at the very end, because it's the function value. The delta x is the height of the trapezoid. So each of these have a delta x, so at the end we also have a delta x. And this is actually the easiest formula to work with when actually working on the problems. And so let me save that up here on the top. And we'll do some examples. So that's our trapezoid rule formula. In the end, that's what we're going to use. So let's look at an example. Suppose that f at x is x squared. We're going to go from a equals 0 to b equals 6. And we're going to use n equals 3 trapezoids. So the picture is y equals x squared, a parabola. We're going all the way to 6. And we're going to use 3 trapezoids. So in this case, we can just see what delta x should be. If I'm going from 0 to 6, then delta x is the length of each trapezoid on the base. And so that's going to be 2. But remember, the delta x is always in formula form, b minus a over n, which in this case is 6 minus 0 or 3, which is 2. So delta x is 2. Each of those is 2. If we're making 3 trapezoids, we're taking 6 divided by 2. In general, b minus a over n. The next step is to write out what are the xi's that we'll be using in our formula. x0 is always a, the very first value in our calculation, which is 0. x1 is the next one in our breaking up of the subdivisions, which you're always going to get by just adding delta x. So all we're going to do is start here and add delta x until we get to the end. So x1 will be 2, x2 is 4, x3 is 6, and that's it. That's xn. We have n is equal to 3, so by the time we get to x3 we should get to the b value, which we do. Alright, so now we've got 0, 2, 4, 6 for our x of i's, and all we have to do is write down our formula. So, what is f at x0? So I want f at 0 over 2. That's what this very first term in the sum is. Plus, what does this say? This goes from I equals 1 to n minus 1. So that's going to be 1 to 2, right? So I equals 1 to 2, because n is 3, so n minus 1 is 2. So we're going to have f at 1 plus f at 2 plus f at, I gotta be careful, I meant x1, f at x1, so let's write that out above. x0 over 2 plus f at x1, let me write this out a little bit more clearly. F at x0 plus f at, that's over 2, x1 plus f at x2, those two pieces right here in the middle are this middle summation, I equals 1 to I equals 2 of f at xi, and then finally f at x3 over 2. Now we're just plugging in for x0, x1, x2, and x3, so that's f at 0 over 2 plus f at 2 plus f at 4, since x1 is 2 and x2 is 4 from right here. And finally, f at x3 is 6, so f at 6 over 2. Now we just have to plug these values into our function, add them up when we're done. So f at 0, since f at x was x squared, that's 0 squared over 2 plus 2 squared plus 4 squared plus 6 squared over 2. Which will make 0 plus 4 plus 16 plus 36 over 2 is 18, which makes 20 plus 18, which is 38. But don't forget that at this point all we've done is found the stuff inside the brackets. We also need to multiply by delta x. So then we need 38 times delta x. But delta x was 2. So that's 38 times 2, which is 76. And that is our estimate for the area under the curve, from 0 to 6 for the function f at x equals x squared, using the trapezoid rule. Now we could actually find that area for this function, 0 to 6 of x squared dx. What happens if we find that area under the curve? X squared integrates to x cubed over 3, integrated from 0 to 6. So we're really just looking at 6 cubed over 3 minus 0 cubed over 3. Well, that's 6 times 6 times 6 over 3, which is 2 times 36, which is 72. So the actual area under the curve is 72. The trapezoid rule estimation gives us 76. Pretty close. If we would take smaller values of delta x, right, greater values of n, more trapezoids, we get a much better estimate. The main point here is that we can make an estimate using a left-hand Riemann sum or a right-hand Riemann sum, but we'd actually use just as many calculations to get a worse result. So this gets us a fairly good result with very few actual calculations. And so we can make a very accurate estimate for the area under the curve using the trapezoid rule with way fewer calculations than using a left or a right Riemann sum. And so next we'll look at the Simpson's rule, which is an even better approximation. It's a little bit harder to understand, the formula and how we get it and where it comes from, but the trade-off is that we get an even better estimate with even fewer calculations involved. Okay, so let's take a look at Simpson's rule, which is again a better way to make an estimate for the area under the curve. It requires very few calculations, so we can use a very large value of n. That is, the number of subdivisions can be very large, but a computer will be able to make calculations very fast. And here's the basic idea. I'm just going to give you the idea. I'm not going to actually prove the formula where it comes from. I just want to describe the formula, show you how to use it, and give you the big idea. The big idea is that rather than using a rectangle like we would use in a Riemann sum, or we would use in the midpoint rule, or a trapezoid like we would use in the trapezoid rule, we're going to take our subdivision. So we have A, we have B, as always. Now we've made some subdivisions, as always, for delta x, and we're going to look at this region, and we're going to say, well, it's not a straight line. So for the trapezoid rule, we approximated it by a straight line. What we're actually going to do is now instead approximate it by a parabola. So we'll use a parabola to approximate. And so essentially what we do is we take the parabola and require that the parabola matches at the endpoints and also matches in the middle. Because given a parabola, if you have 3 points, then there is a unique parabola that will go through any 3 points. So if we want a parabola that matches at both here, here, and here, then there's only one parabola that will do so. And that's the big idea behind what's going on. There's some calculated computations that I'm not going to go through. In the end, we're going to tell you what the formula that we'll get is. Finding the area underneath a parabola is also really easy. Just like if I wanted to find the area under x squared, I just integrate to x cubed over 3. Once I know a parabola, ax squared plus bx plus c, we can do the same thing, integrate it, and it really just comes down to multiplication and addition and subtraction, so a computer can do that for us. In the end, this is the formula that we get. We get f at x0 plus 4 f at x1 plus 2 f at x2 plus 4 f at x3 plus 2 f at x4 and the plus 4, so plus until we get to the very end. And it's a little tricky at this point, so we're going to add up all of these things. The very last one is going to be well, there's going to be 2 at the very end. The second to last will be 4. Again, we're going to go 4, 2, 4, 2, 4, 2. The last one with the 4s and 2s will actually be a 4. And that will be f at x n minus 1. So the second to last one will have a 4. And then finally, just like the very first one has nothing with it, the last one will just be f at xn as well. So we're alternating these 4s and these 2s. It's symmetric in some sense, right? There's a 1 at the beginning, then 4, 2, 4, 2, 4, 2, 4, 2, 2, 4, 2, ends at 4, and then ends with just a constant, a coefficient of a 1 at the end as well. And we also need to multiply by a version of delta x, but the way this works, essentially because we've got 3 points in here, we're taking our delta x and we're dividing it by 3. Because the 3 points make the 3 different pieces in our subdivision. And again, the upside is that we get an easy to calculate formula that a computer can do. It will give us a much better approximation. The downside is that it's not at all obvious why this formula works, and going from here to here does take some work, which I'm actually skipping and just asking you to use the formula in the end rather than develop this formula. One thing to point out here is that it does require an even number for n in order to make this work. I need an even number for n so that we can have a symmetric form here. So this is true. N must be even in order to make these make Simpson's rule work. So let's look at an example. Okay, so let's let f of x equal, how about we say e to the x. Let's do two things. Let's actually use the trapezoid rule. Let's use Simpson's rule. Let's compare them both to the actual area under the curve. Let's go from x equals 0 to x equals 4. And let's say that n is equal to 4, so 4 subdivisions. And let's use the trapezoid rule and Simpson's rule. So for the trapezoid rule first, let's remember our formula. F at x0 plus sum, f at x0 over 2, plus sum of f at xi, where I goes from 1 to n minus 1, plus f at xn, all over 2. So the middle ones don't have anything because they've actually added up 2 versions of it. And then all multiplied by delta x. Now for both trapezoid and Simpsons, because I have the same a, b, and n, the xi's will be the same. So let's use that as our first step. And we'll find delta x first, b minus a over n, which is 4 minus 0 over 4, which makes our life relatively easy here, but the process is always the same. B minus a over n to get me delta x. x0 is always the a value, which will be 0. And then I just add delta x to this until I get down to the b. So x1 will be 1, because this is delta x here. x2 is 2, x3 is 3, and x4 is 4. And we're done. We've got x0, 1, 2, 3, and 4. And these are going to be true when we're using trapezoid and when we're also using Simpson's rule. Okay, so let's actually save those over here. Delta x was 1, x0 is 0, x1 is 1, x2 is 2, x3 is 3, x4 is 4. So if we put these into the formula for the trapezoid rule, that's going to be f at x0, which will be e to the 0, because f at x is e to the x, e to the 0 over 2, plus, again now, if I'm going from I equals 1 to n minus 1, that's 1 to 3, since n was equal to 4. So I'm going to have the 3 terms in the middle for the trapezoid rule. So that's going to be e to the 1 plus e to the 2 plus e to the 3. That's the 3 terms by getting these 3 pieces are now going right inside for the middle. And then the last one is the last one, which is divided by 2. So that's e to the 4 over 2. E to the 0 is 1, so we end up getting 1 plus e squared plus e cubed plus e to the 4 over 2. If you put this into your calculator, you'll find that this is approximately 58.5. Except for, let's not forget that we needed to multiply by delta x. So this is 58.5, but we also need to multiply by our delta x. So let's even put that in there. So still times delta x, still times delta x. delta x in this case is 1, so it doesn't change our result, but don't forget about that. That is 58.5 as our trapezoid approximation. Okay, so trapezoid gave me 58.5 as my estimate. Let's use Simpson's rule. For Simpson's rule, our formula is delta x over 3 multiplied by f at x0 plus 4 f at x1 plus 2 f at x2 repeat the 4's and the 2's until we get to 4 f at x n minus 1 plus finally f at x n. So let's just write that out for what we've got. So since we're only going to x equals 4, delta x is 1. That's 1/3. That's f at 0 plus 4 f at 1, because x1 is 1, plus 2 f at 3, plus 2 f at 2, because x2 is 2, plus 4 f at 3, because x3 is 3. We repeat 4, 2, 4, 2 until we get to n minus 1. This is x of n minus 1, so we're stopping with the 4's and 2's, repeating, and finally we just want f at x4, which is 4. So that's 1/3 times e to the 0 plus 4e plus 2e squared plus 4e cubed plus e to the 4, which is 1/3 times 1 plus 4e plus 2e squared plus 4e cubed plus e to the 4th. Put this into a calculator and you'll find a value of approximately 53.9. So our Simpson's rule is 53.9. Notice that the number of calculations that we did for the Simpson's rule is about the same as for the number of calculations for the trapezoid rule. We had f at 0, f at 1, f at 2, f at 3, f at 4, each of those multiplied by a number, and then each of those multiplied by a delta x. So the number of calculations for Simpson's rule is essentially the same. We've got two different values. Let's finally end with what is the actual area under the curve by using the fundamental theorem of calculus. E to the x from 0 to 4. If I wanted the integral of e to the x from 0 to 4, what we get e to the x evaluated from 0 to 4, which is e to the 4 minus e to the 0, which is e to the 4 minus 1, which, if you put it into a calculator, you'll find to be 53.6, rounded to 1 decimal place. So the actual is 53.6. And so the final point is that the Simpson's rule gets me a much better estimate than the trapezoid rule with really the same number of calculations. So it's harder to understand where it comes from. Just remember that it's coming from approximating my curve by using parabolas rather than a straight line. So it should make sense that we get a better approximation. But really in the end we have to make the same number of calculations, but we get a much better result, which is why it's much better for a computer or a calculator to actually use. Okay, and that's the basic idea for all three of our numeric approximations.